That's good. All right, students, today we're going to learn about solubility. And that means we're going to think about substances that are soluble and insoluble. So we're going to think about substances dissolving and dissociating. That's a new vocabulary word. And the most important thing is you're going to learn how to read a solubility chart so that you can answer the questions correctly. All right, student people, here it is, solubility lecture. We're going to review what you're supposed to do from last class. So what I'd like you to do right now is draw the ions in the solution. That's the cup right here, the cup of water, for both of these two equations, for both of these two formulas right here. Pause the video and draw those out and write the equations, and I'll show the answer to you shortly. All right, students, I'm about to reveal the answer to the first problem. In the first problem, you should have drawn this in the container. There are 2 ammoniums and 1 carbonate polyatomic ions in the container, and this is the equation that you need to have written. Everything matters. You need to be drawing the S for solid and the AQ for aqueous solution, showing that the solid dissolved in the water. AQ means aqueous, means there's water in there. Okay, here comes the second answer. Here's the second answer. In the container, you should have 3 sodium ions with the 1 plus written there and the 3 minus written there for the phosphate ion, polyatomic ion, the phosphate polyatomic ion. And here's the entire equation. Everything matters in there. Oh, I forgot to put the little 3 minus. You have to have the S for solid and the AQ for aqueous and the charges on this side, but not on this side, because this is a dissociation equation, meaning the solid, when placed in water, dissociated into its ions, and that's what this chemical reaction shows. All right, students, if there's any questions about that, let me know. You are definitely responsible for drawing subscripts and superscripts in your homework assignments, in your classwork assignments correctly, or else your assignment grade will be lowered. There they are, written on the computer with the correct subscripts. Oh, and there's this little thing that we have to write down here. We have to do the subscript AQ. So that should be written for every single one of the ions in the equations. Okay, vocabulary review. What is soluble, insoluble, and aqueous? So soluble just means a substance that's able to dissolve. Insoluble means a substance that is not able to dissolve. And then finally, aqueous means that the substance is dissolved in water. It has that little AQ symbol right next to it. One moment. Okay, so let's go down here. Which compounds are soluble in water? So at the end of this lesson, you, the student, should be able to determine if a compound is soluble or insoluble in water. You've already written down these vocabulary words from last class, so you don't need to write them down again unless you haven't already. Okay, let's continue on. Will salt, NaCl, dissolve in water? Well, let's take a look. Dissolving is a relationship between the solute and the solvent. In this case, the NaCl is the solute and the water is the solvent. When you put them together, that makes a saltwater solution. So water can dissolve salt, and salt can dissolve in water. It's a relationship between the salt and water that causes the dissolving to happen. So let's start by taking a look at the water first. Let's take a look at the solvent, water. Okay, here are 3 different models of the same thing. These are all water molecules. And what you notice is that there are the same ratio of elements in each of them. There's one oxygen and there's two hydrogens. And there's something else that you should definitely notice, and that's this little negative sign right here next to the oxygen. You notice how the negative sign is next to the oxygen, and the positive sign is next to the hydrogens. Okay, that's important to note and pay attention to, because that's going to increase our understanding of why substances dissolve. So here's a new vocabulary word. Please write it down. It's called polar. What polar means is an unequal distribution of charge in a molecule. So the reason why there's unequal distribution of charge, meaning that there's a negative side to this molecule and a positive side of the water molecule, is because oxygen is more electronegative than hydrogen. And that means that oxygen has a better ability of attracting the electrons, which are negatively charged, to itself, to its nucleus, which causes the oxygen side of the water molecule to be more negative, and the hydrogen side of the water molecule to be more positive, because less of the electrons are hanging out around the hydrogen side of the molecule. So polar is kind of like, the Earth has a North Pole and South Pole. They're opposite sides. And that's kind of what polar means. It means there's two different sides. Like, have you ever heard polar opposites? It's kind of like that. Or have you heard in the news when they say it's polarizing? It means a group of people are thinking one way and another group of people are thinking completely another way. And there's a gap in between their thinking. And that's why conversations can get really heated sometimes, is because people are polarized. People's worldviews are polarized, and they become polar opposites in their thinking. So when we think about the word polar, that's what we're thinking about. Two opposite sides within the same molecule. Okay, water is a polar molecule. The oxygen is more partially negative, and the hydrogens are more partially positive. Please write this out. If you don't write this out, that's your bad. It's proven that writing improves memory retention and learning. So please do that. Okay, the north, the positive side, and the south, the negative side of magnets are attracted to each other with an electromagnetic force. It's the same with molecules, because opposite charges in molecules attract. Positive and negative charges attract each other. So see down here, there's this picture of magnets. You can see that they attract each other, the opposite sides. But if you put the like sides together, they kind of repel each other. If you've ever played with magnets before, you've felt this electromagnetic force of attraction or repulsion. It's kind of amazing if you take a moment to stop and think about it. Like, there's this invisible force that is causing the magnets to repel or attract, and you can't see it, but it's there. You could like put your hand through it. There's nothing there, but there's like a force causing them to pull together, like they're attracted by a string or something like that, like they're connected by a string. Okay, so if we could scroll back up and look at the water molecule, you could see that in three-dimensional space, the water molecule is oriented like this, with the negative side here and the positive side here, and another water molecule comes along and it moves closer to this water molecule. What will happen? The negative side of this water molecule will attract to the positive side of this water molecule. And so this water molecule over here should actually kind of be turned and look like this, so that the negative side of this water molecule is attracted to the positive side of this water molecule that's next to it. Okay, so water is like that. A bunch of water moves past each other, but they're attracted to each other like that. Okay, so if we think about, that's about the solvent. The water is the solvent. So you just learned something about water. The thing that you're going to learn now is about NaCl. So molecules like NaCl that dissolve in water are actually attracted to water with more force than the element or molecule they are initially bonded with. What that means is that the sodium ion and the chloride ion are more attracted to the polar water molecule than they are to each other. So what happens is that when you put salt in water, the salt will dissociate and break apart, because the water is so powerful, because the electromagnetic force of attraction is so powerful with the water. But in the case of silver chloride, AgCl, the silver and the chloride are more attracted to each other than to the water molecules, so they stay together. Silver chloride does not dissociate in water. Silver chloride is insoluble in water. It does not dissolve in water. So yes, that could be confusing to you. Sodium chloride dissociates and dissolves in water. Silver chloride does not dissociate and dissolve in water. It will remain a solid and you'll have to put that little S in the chemical equation, and NaCl will dissolve. So you have to put an AQ for aqueous, showing that it's dissolving in water. Please go ahead and take some time to catch up and write all of this stuff. Pause the video if you need to. Sodium chloride breaks apart in water to form sodium ion and chloride ion. This is due to the fact that the partial charges on water are more attracted to the sodium ion and chloride ion than the ions are attracted to each other. It's all about love and attraction. Oh, yeah. So here's 3 pictures of a beaker, and it's a time lapse. So this is when you pour a bunch of salt in water. You can see that there's like a pile of salt. But if you mix it, then you can see the salt starts to dissolve, right? The salt starts to dissolve. And this is a molecular look of the salt dissolving. Okay, so right here, this group of green and purple, that's the sodium chloride, and all of this above it, that's the tiny water molecules. So after you mix it, what ends up happening is the water molecules start to pull apart the chloride ions, which are green, and you can see that the hydrogens are facing the chloride ion. And you can see that the sodium ion, the oxygens from the water molecule are facing the sodium ion. So why are they orienting themselves in 3-dimensional space like that? Well, the answer is because of electromagnetic forces of attraction. That's just simply meaning like positives and negatives attract each other. So if you zoom in on this picture even more, the hypothesis is that it looks like this. You see the water, these are water molecules surrounding the chloride ion, and the positive side of the polar water molecule is attracted to the negative chloride ion, while the negative side of the polar water molecule is attracted to the positive sodium ion. So you can read below that slightly positive hydrogens are attracted to the chlorine anions, slightly negative oxygens are attracted to the sodium cations. Anions means negative ions, and cations means positive ions. There you go, Lily. Okay, so that's a lot of what you just learned. You learned a lot of things just now. I hope you wrote down those vocabulary words and you understand a little bit more about water and about substances that dissolve and substances that do not dissolve. So how do we know what substances are soluble and insoluble? Well, here comes the most important part of the lesson. We have a resource that will tell us which molecules will not break apart in water, meaning they're insoluble. And the resource will tell us which molecules are going to break apart in water. That means they are soluble. Okay, so let's go ahead and take a look at that resource. All right, students, on Canvas, in important resources, page of links to resources, if you click it, right down at the bottom, it says Solubility Chart of Common Inorganic Compounds in Water. You're going to need to use this for this unit. Get used to opening it up, maybe print it out. That'd be great. So let's open this thing. This is what it looks like. Maybe I could zoom in a little bit. Okay, so the way to use this chart is to first know that this chart is meant for you to determine which molecules are soluble or insoluble. Okay, and the way that you should do that is first by looking at the anions. That's the negative ions that are usually written second in the ionic compounds. So if you look at the anions, it will tell you which cations are soluble or insoluble. So the directions, again, are this. This chart tells you which compounds are soluble and insoluble. The way it works is you should first look at the anions in the middle, and whichever anion you're working with. For example, if we're looking at bromide, you should take a look at that, and then ask yourself, what is bromide connected to in the formula? Well, if it's silver bromide or lead bromide or mercury bromide or titanium bromide, that means that molecule is insoluble and will not break apart in water. If the bromide is in a formula with any other cation, meaning anything else besides silver, lead, mercury, and titanium, that means that that molecule is soluble. Let's go ahead and try a few problems together. Okay, let's take a look at how to read the table and do a few examples. So the directions are to write the formula for the compound that forms from the cation and anion. That's over here. You write the formula in this box. And we're going to also mark an X for either soluble or insoluble. That's right here or right here. So in the first example, we could see that silver acetate is insoluble, and this is how you write the formula. Okay, so there's one answer for you. Let's go ahead and look at why it's insoluble by analyzing the solubility chart. So here's a solubility chart, and where is it? Sorry about this. There we go. Okay, so here is the anion. Let's do that again. Here's the anion, CH3COO. So we found it right here at the top. And look, it's connected to silver. See, it's connected to the cation silver. And so we can mark an X in the insoluble box because silver acetate is an insoluble molecule. Okay, let's do the next one. Sodium acetate. So the directions are to look at the anion first on the solubility chart and then analyze the cation. So right here, we're working with acetate. And if we look over in the insoluble column, sodium is not located there. But in the soluble column, it says almost all cations, and that's including sodium. So for this answer, we can put an X near soluble in the soluble chart. So how do we write the formula? It looks like this is a +1 charge and a -1 charge, meaning you only need one of each to balance out this formula. And let's make the subscript. Oh, never mind. We don't need to do that. Okay, next one. Iron iodide. That's the name of this formula. And it looks like there's a +2 charge and a +2 charge on the cation and -1 charge on the anion. So your formula should look like this. Fe, I, and there needs to be 2 iodides. That's iron iodide. So let's go ahead and look at, on the solubility chart, let's look at iodide and then see if iron is in the insoluble category column or the soluble column. So let's find iodide. That's the next one down. Here it is right here. And if you can see, iron is nowhere to be found in the insoluble column, which means iron belongs in the soluble column. So iron iodide is, you guessed it, soluble. And that's how this chart works. Go ahead and try and answer these next ones on your own, but I'm about to give you the answers, so pause the video if you need. So let's work a little bit faster. Lead iodide. This is the formula for lead iodide. And is it soluble or insoluble? Let's check the chart. Iodide says that if it's bonded with lead, Pb, that means it's insoluble. So we're going to go ahead and mark the X on insoluble. Next one is silver nitrate. It's +1 charge and a -1 charge, so we only need one of each. So it should be AgNO3. And we're looking for the nitrate on the solubility chart. We're not looking for the silver first. We're looking for the nitrate. So let's look at the anion first. The anion is nitrate located right here. And look at this. No cations react, meaning all cations are soluble. No cations react, all cations are soluble. That means anything that is bonded to nitrate is in the soluble column. So we're going to go ahead and mark soluble. Okay, next one is copper sulfate. It looks like there's a +2 for copper and a -2 for sulfate, so they balance each other out on the balance beam. And that means you only need one of each, so we got copper sulfate. And let's go ahead and look for sulfate on the solubility chart. Sulfate's located right here. And let's see, is copper written in the insoluble column? No, copper is not located here, which means copper is considered copper bonding with sulfate is considered soluble because copper is in the all other cations category. So that's going to be soluble. Finally, barium hydroxide. That's barium hydroxide. Looks like there's a +2 here and a -1 here, which means we need 2 hydroxides to balance out the charge of 1 barium. So how we write the formula looks like this. 1 barium. And since hydroxide is a polyatomic ion, you must include the parentheses around the polyatomic ion. Okay? That's how you write barium hydroxide. You have to write it like that. Let's go ahead and look at the solubility chart for hydroxide. Let's find OH. Where's OH? Oh, it's way down here. Hydroxide's right here. And it says reacts with most cations. Okay. So it reacts with most cations. So which cations does it react with? Meaning which cations is it soluble with? Well, it's soluble with ammonium, and it's soluble with all cations in group 1. What is group 1? Let me show you. So students, when it says group 1 on the solubility chart, it's referring to the columns on the periodic table. So this is group 1, this column is group 2, and this column is group 3 right here. So it goes on and on like that. That's what it means by group 1. So we're looking for barium, right? So we're looking for is hydroxide bonding with barium. And barium's not in group 1, but barium is written right here. There's barium right there. And it's in the soluble category. So when barium bonds with hydroxide, like in the problem we're trying to solve, you can put a check mark next to the soluble box. So we're putting it there. Yep. These would be the answers. Oh, these would be the answers to these problems. Okay. That's basically what your homework's going to, or your classwork's going to be on. Since molecular formulas are made from cations and anions, those are the positive ions and negative ions, we can determine solubility by using the formula only. So it doesn't have to look like this, the questions don't have to look like this box. You don't have to know what the cation and anion is. You can just look at the formula and determine whether the substance is soluble or insoluble, because you can see that the formula right here is made up of silver and it's made up of acetate. So you can determine that that's insoluble. Or for example, here you can look at the formula and see that this is made of lead and iodide, meaning that you can determine that this is insoluble, and so on and so forth. You can see that this is barium bonding with 2 hydroxides, so you can determine that that's soluble. So if I just give you the formula, I'm going to put these answers in here soon. All right, students, let's take a look at this chart to see if we can fill this one out. This one says we need to mark if it's soluble or insoluble. This time we'll just be writing the word. And here's the formula given. And here we're going to write the ions in the water if present. So basically what your visualization is, what you should do while you're visualizing is think that you're going to be putting this substance inside of water. And you're going to determine if that substance is soluble or insoluble. And you're going to write down the ions if the substance dissociates into ions. So let me show you how to do this one. So let's go ahead and analyze silver and chloride. Chloride is the anion, so that's what we should look at on the solubility chart. Chloride's written right here, and silver is on the insoluble chart, is on the insoluble column, so we can know that this is insoluble. Okay? So we can say insoluble right there. Just write it out. You don't have to capitalize the end. That was a mistake. Okay. So what do we do for ions if present? Well, since silver chloride is insoluble, that means there are no ions inside of the cup of water. So we could write none. That's highlighting. We don't need to do that. Let's change that real quick. Okay, so there are no ions present in the cup of water when you place silver chloride inside of the water because silver chloride is insoluble. Let's take a look at the next one. Barium sulfate. Sulfate is the anion, so that's what we should look for on the solubility chart. Sulfate is located right here, and we're looking for, what is it again? Barium sulfate. So we can see that barium, located right here, is in the insoluble column. So barium sulfate is insoluble. Okay, so we got to write insoluble right here. And then over here, are there ions present? No, there are no ions present because barium sulfate is insoluble and it does not dissociate when you place the barium sulfate in water. Let's take a look at the next one. Magnesium sulfide is the name of this. Magnesium sulfide. So let's look at sulfide. That's the middle anion. Here it is, sulfide right there. And it says reacts with most cations. So now we need to look at the other column to see if it reacts with that one. So it says that it reacts with ammonium and also all the cations of group 1 and group 2. So let's find out. Is magnesium part of group 1 and group 2? Yes, it is. If you take a look at column 2 on the periodic table, you'll notice that magnesium is part of that column. So this is soluble. And are the ions present? Yes, they are. And the way that you have to write the ions looks like this. Oh, one moment. Mg with a superscript of 2 positive. And you're also going to be writing the sulfide with a superscript of 2 negative. And that's how you write these answers. Last problem is lead hydroxide. So what we need to do is look at hydroxide on the solubility chart first. So there's hydroxide on the solubility chart. It says it reacts with most cations. So let's figure out which ones hydroxide reacts with and is soluble with. So it says that ammonium is soluble with hydroxide. It says that the cations in group 1 are also soluble with hydroxide. It also says that calcium, barium, and strontium ions are soluble with hydroxide. None of those are lead. None of these examples in the soluble column are lead, meaning that lead hydroxide, which is this molecule, is insoluble. So that's insoluble. Okay, are there ions present in the cup of water if the substance is insoluble? No, there are no ions, meaning that lead hydroxide is a solid. So you could even say that barium sulfate is a solid. You can say that the AgCl is a solid. Now over here, you can imagine the magnesium sulfide. That's actually also a solid, but let me explain. That's a solid before it's placed in water. So over here on this side, the subscripts that you should write is AQ, meaning that it's dissolved in water. It's dissociated inside of water. Okay, lots of new vocabulary being thrown around, and it's your responsibility to know all those vocabulary words. All right. All right, students, that's the gist of the entire lesson, but letting you know what this is going to get into next time so that you can become an expert at this lesson. It looks like this. We're going to be looking at precipitate equations. Remember what a precipitate is a chemical reaction between 2 liquid solutions resulting in a solid that forms. So what it looks like is if we take silver nitrate and react it with sodium chloride, this is a double replacement reaction, so the silver will bond with the chloride and the sodium will bond with the nitrate. So here's the silver chloride over here as a product and the sodium nitrate. Well, if you see in orange that the silver chloride is insoluble, meaning that if you mix these 2 aqueous solutions that look like liquids, if you mix them together, silver chloride will precipitate out of the solution and look like a solid forming. The sodium nitrate will not do that though, because remember, sodium nitrate is soluble while silver chloride is insoluble. Okay, so students, if you look over here, this is kind of what the reaction looks like when you combine the, what was it again? It was silver nitrate and sodium chloride solutions. So you can see the silver nitrate and sodium chloride solutions are both clear liquids. And when you mix them together, a solid white precipitate forms. in the solution. All right, students, good job taking all those notes. This is one of your last and final units in chemistry class for the whole year. So finish the chemistry class really strong and have a great day.